Hello everyone, this is Kyle Liang. I'm a graduate student at the Silicon Synapse Lab at Northeastern University. Here I'm presenting our recent work on rough terrain locomotion and unilateral contact force regulations with a multi-modal leg robot. This is joint work with Eric, Andrew, Parvin, and Professor Ramazani. Despite many accomplishments by leg robot designers, state-of-the-art bipedal robots are prone to falling over, cannot negotiate extremely rough terrains, and cannot directly regulate unilateral contact forces. Our objective is to integrate the merits of leg and aerial robots into a single platform. Here we introduce our thruster-assisted bipedal robot Harpy. This robot has projected weight of 5.5 kg and has 6 degrees freedom on the body, 3 on each legs, resulting in 12 degrees freedom. The thruster feature on this robot can be used to assist walking over rough terrain, frontal dynamic stabilization, and regulate ground reaction forces using optimization-free constraint separation algorithm. We will briefly introduce the existing work related to leg locomotion on rough terrain. Among varying leg robotic platforms, hexbots and quadrupeds, such as CMAU's hexbot, little dog, mini cheetah, and animal, those are typically much more stable compared with bipedal robots when walking on rough and uneven terrain. For example, DARPA Learning Locomotion Program utilized the Boston Dynamics Little Dog robot to navigate complex terrains unrehearsed. In a more recent example, Animal is capable of navigating rocky terrain, grassy areas, and stairs. Bipeds, on the other hand, have difficulty in navigating complex terrains. Even humans have difficulty in navigating rough or slippery surfaces, despite having great flexibility and sense of balance. This motivates us to explore the multi-modal locomotion. Here are examples of multi-modal robots. Robots with terrestrial and aquatic mobilities, such as Salamandra and Velox. Those can move both on the ground and in the water through the same appendages. Robots with terrestrial and aerial mobilities, examples like Dollar and High-Tech, those can fly in the air and move on the ground. The multi-modal capabilities of these robots allow them to be much more adaptive and flexible to a diverse set of environments. There is not much multi-modal locomotion application for bipeds, and our robots will combine the aerial locomotion using thruster to assist bipedal robots in navigating rough terrains. Based on these concepts, we want to explore the capabilities of thrusters through simulation. The thruster featured on Harpy robot can be used to assist locomotion through posture stabilization as it navigates a rough or slippery terrain by stabilizing the front and side dynamics. And since we can fully control some under-actual states by addition of thruster actions using optimization-free constraint separation algorithm, explicit reference governor to regulate ground reaction forces, which typically requires optimization technique. Thruster actions can also be used to assist in jumping or flying over difficulty to navigate terrain, which greatly improve the adaptivity. Here are some simplified assumptions for the simulation. All mass is concentrated at the center of body and motors. Linkages connecting the body and motors are massless. Thrusters can provide forces in any direction and their dynamics are not included. Therefore, we can obtain our system dynamics using Lagrange formalization. The derivation is skipped here. The first inputs including the ground reaction forces UG, joint actions UJ, thrust actions UT, in which the derivations would be discussed in a moment. This gives the robot with 12 degrees freedom and 8 controllable inputs. The ground reaction force UG is calculated using a unilateral compliant ground model with an undamper rebound and a strip friction model. In the Z direction, when the foot penetrates the ground can be viewed as a stiff spring and damper with undamped lifting. The frictions in the X and Y directions are defined as the equation and figure show, which itself also depends on the normal force. To show application of thruster-assisted walking in a robot, we constrain the system dynamic in the XZ plane and use a first-order visual curve to describe the foot end trajectory in the body frame. Here are the results of walking pattern during one gait cycle. Figure 1 is the trajectory for the stance leg and Figure 2 is for the swing leg, which are switched alternately for the left and right legs. The corresponding joint actions uj are found through inverse kinematics. This planar gait is not stable in a full model implementation. For thrust control design, they are used to stabilize yaw and roll angles by generating moments for zero references, and the additional thrust actions are used to tracking body trajectory, which is set up to be a constant forward velocity at 0.3 meters per second. Therefore, the thrust action uj is a combination of both inputs. In this work, we achieve the regulation of ground direction forces using explicit reference governor and optimization-free constraint certification algorithm through thrust manipulation. Our goal is to manipulate the applied reference as close as possible to the target reference while satisfying the constraint equations which are found in the target reference. The constraints including the friction cone constraints and the minimum normal force to avoid abusing of thrust forces. We can adjust the reference based on this Lyapunov equation and using the following update law, which consists of three components. This is a pseudocode for the ELG algorithm determining the three components for the reference updates. HR is a constraint equation using the target reference, and HW is a constraint equation using the applied reference. VR represents the rate convergence towards the target reference, and it is zero when both target and applied references violate the constraints. Vn represents the rate convergence to manipulate the applied reference towards the positive constraints value when both references violate the constraints. Vt represents the rate convergence along the null space of the violating matrix entries, which allows the applied reference partially tracking the target, as changing in the null space does not affect the value of the constraints equation. And the resulting rate of change of the applied reference is the sum of the three components. The ELG is hard to directly implement it in the full model. This figure shows the evolution from the full dynamics on the left to a 5-body and 3-body pendulum model, and finally reduced to a variable length inverted pendulum model on the right, doing single support through the simplification of virtual leg and compilation of the mass. This reduced order model is used for the robot doing walking with ELG. The inverted pendulum model is fully actuated by the addition of thrust forces. The constraint force is set up to keep leg length equal to the leg configuration. The constraint force forms the ground direction forces that depend on the body position, center pressure, and thrust forces, which is also a function of target reference. These ground forces form the friction cone constraints and can be expressed as defined in the target reference for ELG implementation. The thrusters can also be used in navigating rough terrain by simply flying over obstacles. However, since two thrusters are symmetric to the mass of the body, the pitch dynamic is not controllable. An MPC framework is developed to regulate foot end positions and to ensure proper landing posture. We are using a 2-body pendulum model as a reduced order model for the MPC. The MPC using the following optimizer, the cost function includes errors in trajectories and the rate of change of control inputs. It is subject to the dynamics of the roll, and the hip center angle is regulated based on the pitch and the landing angle for adjusting the leg during the landing. We simulate the result in MATLAB using the interpolating method and RK4 scheme. The MPC and the ELG filters are simulated using a zeroed hold at a frequency 20 times smaller than the numerical integration to better capture the behavior of the onboard computer in Harpy. The red arrows around the robot are the ground direction forces, and the blue arrows are the thrust actions. The robot is jumping over the first obstacle through a ballistic trajectory, and it lands to resume walking for a second jump. You can see in both cases, the robot does not slip and lands smoothly. This figure is part of the simulation data of the ELG. While the constraints equations are violated using the target reference shown in red, we can see the constraints equation using the ELG manipulate reference shown in blue satisfy the constraints. At the beginning, due to the sudden change in the foot position, both references violate the constraints. The convergence rate of Vt bring the applied references right away from the violating constraints. After 10 seconds, the convergence rate Vn allows the applied reference partially tracking the target reference while it violates the constraints. And when the target does not violate the constraints after 11 seconds, the convergence rate Vr allows the applied reference track close to the target. In conclusion, we propose a thruster-assisted bipedal robot, and through the simulation, we demonstrate a robust multimodal locomotion using thrusters. We present a RERG framework for computationally inexpensive ground reaction force constraints application. This is the end of our presentation. Thank you for listening.